Good day, ladies and gentlemen. Today is graphing with slope and y-intercept, and it is the second day we're doing that skill. Today we're going to look at some equations that aren't in slope-intercept form, and we're going to have to do a little bit of algebraic manipulation before we actually graph the relationship to see what the slope and y-intercept are. In order to do that, it's a good idea to review some of the concepts we've gone over so far. So in the do now, we have a question where we're asked to write an equation of a line going through the points 2, 2, and 3, 5. So there's a couple of ways to interpret that. One is to suggest that if we were to make a quick graph sketch of it, we would consider that 2 units of time from now along the x-axis, 90% of the time the x-axis is time, we'd have something that measured 2 units high, whatever that might be. That might be 2 pounds, 2 inches, it could be $2, it could be anything that we're measuring. And we could also further suggest that 3 units of time, that relationship is going to go up to a measured amount of 5. So 3 units of time from now, it's going to go 2, 3, 4, 5. And if we had a little sketch of that, we might be able to say, well, if it's starting at 2, 2, and it's ending at 3, 5 during this observed period of time, aren't we able to suggest that the measured amount, the y variable, whether that's inches, money, or pounds, has gone up 3? And couldn't we further suggest that happened over 1 unit of time? And wouldn't the rate of change simply be 3 over 1? 3 measured amounts increasing every 1 unit of time. In addition to being able to look at a graphical interpretation and identify the slope and y-intercept, we could also look at a table, which we have done as well. We could suggest that in a table we have 2 units of time from now the relationship measures 2, and at 3 units of time from now it's going to go up to 5. Typically tables are organized as x, y, and we would notice that if we observe the rate of change is change in y over change in x, we have an increase of 3 occurring every 1 unit of time. And our rate of change, triangle y over triangle x, could be 3 over 1. In addition, if you stay in your table for just a moment, you could find the second most important variable in a linear relationship, the beginning amount. The beginning amount is a value at time 0, so we could undo the addition of a unit of time and go back 1 unit of time, and we would undo the addition of 3 over and over again, the rate of change. And we'd find out that 1 unit of time ago, if we subtract 3, this relationship actually measured -1. And we can go back to time 0 by subtracting 1 unit of time again, and additionally in our y variable, our measured amount, subtracting 3. And we'd find out that at time 0, this relationship measured -4. And having those two pieces of information from an informal investigation, we can find out that our measured amounts y are going up 3 over and over again x number of times starting at -4. Or if you prefer, you could say y equals -4 increased by 3 over and over again x number of times. Now, when we do those same steps or that same investigation formally, typically what we do is we write out the relationship that we're trying to describe, in this case a linear pattern. So we know the formula, or the most popular formula, is y equals mx plus b, slope-intercept form. And the two most important variables are m and b. And m, the rate of change in y over change in x, or rise over run, can be formally processed through the difference in y's over the difference in x's. So we would label our points x1 and y1, and we would label our second point x2 and y2, simply meaning the first observed time and measured amount along with the second observed time and measured amount. And we could substitute into our slope formula appropriately, setting it up with parentheses for substitution, and identifying the amounts that belong in the appropriate position. So in the numerator, we want to take our final measured amount of 5 and subtract away our beginning measured amount during that interval of time or in between those times. And in our denominator, we want to take our final time we measured and subtract out the beginning time we measured during this interval. And if we do that appropriately, we get 3 over 1, exactly what we observed informally. Formally, if we wanted to determine the y-intercept, formally just means using a formula, we could once again rewrite our most popular form, or formula for a linear relationship, y equals mx plus b, slope-intercept form, and we could appropriately substitute in for y, m, and x. It doesn't matter which point you use, 2, 2 is easy, you won't mess up the substitutions. This relationship measured 2 as a result of going up 3 at a time, twice, starting at b. So we're able to say that 2 is the result of 6 being added to our beginning amount. So if we undo that addition of those two repeated additions of 3 or 6, we find that the beginning amount must have started at -4. And we can write this relationship as the measured amounts are a result of starting at -4 and adding 3 over and over again x number of times. I'm going to skip Roman numeral 2 for right now, but I'll jump to Roman numeral 3, where we have some context added to the skill that we're working with. And we're asked to write, or we're asked what is the function rule for the following table. And since we're working with linear relationships, function just means a useful equation. And the only one we've learned so far is a linear pattern, y equals mx plus b, so that's what we're talking about. And the two most important variables are m and b. M could be determined formally as y2 less y1 over x2 minus x1, the difference in measured amounts over the difference in time. Or if you prefer, and more efficiently for this relationship, as it's shown in a table, you could simply determine the change in y or the measured amounts over the change in x, the change in time. Now what you'll notice is that the cost appears to be going up $4 every time we add a CD to our purchase. So it appears as though the CDs are increasing at $4 per time. Once we know m, we have to go back and get b. And in order to get b, the beginning amount, the value at time 0, we would use that formula y equals mx plus b and substitute in for y, m, and x. It doesn't matter which point you pick throughout the table, so to be different, I'll try 3, 18. If you're not sure where to start a relationship or an equation, good place to start is with the total. So in this instance, 18 gets substituted in place of y. There's the total cost, which is a result of purchasing 3 CDs for $4 a piece, starting at B. So 18 is the result of adding 12 to our beginning amount. If we subtract out that 12 from the beginning amount, we'll find out that this relationship started at 6. So we're able to say that the y variable cost, I'm going to use C instead of y, that's more in the context of the question. It helps me to better see what I'm describing in this repeated addition pattern. So the cost is a result of it being $4 per DVD. I'll use D for DVD instead of X. And starting at 6. Or if you prefer, you could use the commutative property of addition to say that CDs are going to be the result of starting at $6 and paying an additional $4 for every DVD you purchase. It's interesting because in this particular relationship, you might say, well, what's that $6, Tooch? Where did that come from? And if you've ever been a part of any online resource club, a lot of times when you're purchasing things in quantity, you usually have to pay a membership fee for that discount. So maybe there's a $6 fee to belong to a DVD club or a $6 fee to belong to some online subscription. And then every time you purchase a video or a movie or something else, you're paying $4 additional each time. So this could have also been done informally. You could have extended your table and you could have tried to determine the value at time 0 by undoing the repeated addition of 4. And we undo addition with subtraction. And you simply could have subtract 4 as you went back 1 unit at a time. And you would have found out that the beginning relationship was 6. And all processes that are correct are acceptable. We like you to learn each and every one of them so you can choose which one you prefer at any point in time. For question number 1 in today's specific skill, we're going to be continuing graphing linear relationships in slope-intercept form by identifying the 2 most important variables m and b and then applying them to a pictorial representation of the repeated addition pattern. And the most important thing you're going to have to learn today is that in order to graph in slope-intercept form, your equation has to be in slope-intercept form. You have to do what we call solve for y. So if you notice in question number 1, it says y less 4x equals 2, and that's not the appropriate presentation we would like to identify m and b. We need to determine what y is equivalent to based on all the quantities in the relationship. So to determine what y is equivalent to, our relationship must be presented as y equals. Now in this instance, because we have to subtract 4x from the y quantity, we have to move or remove it. And we can add whatever we want to an equation so long as we do it equally to both sides. So we're going to add positive 4x's to both sides to eliminate the subtraction of 4x from y. That's going to leave us with just y as the expression on the left, positive 4x and negative 4x will cancel. And in the expression on the right, we either have 2 plus 4x, which is just 2 plus 4x, or if you prefer, you can rewrite it as y equals 4x plus 2 using the commutative property of addition so you don't get confused when you want to identify the m and b variables. Y equals mx plus b. M, the rate of change, is 4. We're repeatedly adding 4 over and over again to the beginning amount of b, which is equal to 0. The relationship, b, which is equal to 2. The relationship measures 2 at time 0. So 2 important facts to consider as we tie together all the different observations in this linear relationship unit. One is that, well, Tooch, I know that we're calling 4m the amount we're multiplying x by, but you keep saying we're adding 4 over and over again. And it's important that you recognize that multiplication is just repeated addition. So yes, we are adding 4 over and over again. And yes, we are calling it m because it appears that we're multiplying x by 4, which we are. But again, multiplication is just repeated addition. Also, we're saying that b is the value at time 0, which technically means that if we substituted 0 in place of x, and we evaluated the expression, anything times 0 is just 0, and 0 plus 2 is 2. So this value at time 0 equals 2. That's where we're getting 0, 2 from, and that's why that's applicable in this instance. When you graph in slope-intercept form, it's important to begin at the y-intercept, the value at time 0. That's going to be our x1, y1. We're going to identify that at time 0, the relationship measures 2. And then we're simply going to follow the slope. And following the slope rise over run means that we're going to increase or add 4 to this relationship every 1 unit at a time. So we're going to go up 1, 2, 3, 4, and move to the right, forward in time. 90% of the time, the x-axis in time. We should have labeled our axes, by the way. And again, we're going to go up 4. We're going to increase 4 measured amounts and go over 1. It's always a good idea to get points in the back of the pattern. So to get points in the back of the pattern or prior to time 0 or in the past, we want to undo addition. And we're going to undo addition with subtraction. So we're going to go down 4 and to the left 1. I like to put a tiny little x there to indicate that I'm working backwards. Down 4 and to the left 1. Down 4 or decrease of 4 measured amounts as we go backward 1 unit at a time. You should then take a straight edge, a ruler, or the side of your calculator, or if you have to get creative and find something in your house right now, something that would allow you to make a perfectly straight line. And when we make that perfectly straight line, we want to make sure that we hit all the points as best as possible. We should have arrow tips on either end, indicating that the relationship goes on forever if our graph was actually larger. And you should always label it. This is the relationship where our y values are starting at 2 and increasing by 4 over and over again x number of times. Cool. There's your training question. Here's your context question. And in the context question, ladies and gentlemen, the more important ones, we're told that the temperature is a function of time, which means the temperature is a result of, or is a useful equation that's going to be able to be predicted based on time. And we want to solve for t in this particular relationship. Careful to note that t is temperature and not time. That was a little tricky. I probably could have picked better variables. And we're going to graph our results. So twice the temperature is equal to 30 per hour plus 90. And in order to graph this in slope-intercept form, we need to solve this for the y variable. The y variable is t once again. Good idea to label our axis x comma y. The x variable in this case is hours, which again is a measure of time, so I could have chosen better variables, but we'll survive. So we're solving for the y variable. And in order to do that, we don't want twice y equal to the expression. We want just one y. So we're going to undo the multiplication of 2 by dividing by 2. And in order to divide the entire expression on the right by 2, it's a good idea to show that you need to divide both terms by 2. Now, technically, what you could have done is you know that multiplication is the same as, you know that division is the same as multiplying by the reciprocal. So you could have had the awareness to say, Tooch, if we're dividing by 2, aren't we really multiplying by a half? And if we're multiplying by a half, shouldn't we really multiply the entire expression on the left by a half? And wouldn't that require us to distribute to both the terms? And half of 30h is going to be 15h, and half of 90 is going to be 45. So this is going to come out to 2t, equals 15h plus 45. And that's why it is important for us to understand that when we divide out the coefficient of 2, we must divide both terms, because technically we're distributing a half to the entire expression. So if we actually do it by dividing by 2, we do in fact get t equals 15h plus 45. It's a good idea to identify M and B, be an active learner. And being an active learner would mean actually writing M equals, it appears to be going up 15 degrees every 1 hour, and B equals starting at 45. And technically, we should write 0, 45. At time 0, the relationship measures 45. That is our y-intercept that we're able to graph from. And we're going to increase by a rate of 15 degrees every hour. Now, when you look at the scale of the x-axis, conveniently, it is created for you in increments of 15. So going up 15 doesn't mean we count 15 boxes. It simply means we would go up 1 box. That's going to represent an increase of 15 degrees. So as we go up 1 box, and I fight to find the appropriate pen, from a beginning amount of 45 to 60 degrees, we need to go over 1 hour. And we can go up 15 degrees, and again over 1 hour, and we can continue that pattern across our graph. We would then need to get a straight edge, connect the points, and include an arrow tip at either end. So this is kind of a fascinating investigation. I think this is what I usually describe as my desert scenario. So the desert, although hot during the day, gets very cold at night because it has no real atmosphere, so all the heat just leaves. But then once the sun comes out, it increases rather quickly. And you can see that in this particular relationship, it's suggesting that the desert would go up by 15 degrees every hour. And we're able to write that our temperature is going to go up, or start at 45 degrees and go up 15 degrees every h number of hours. You should always label your graph so people know what you're describing. In part A, it says, based on the graph, what would the temperature be after 6 hours? So based on the graph means we should specifically be making our observations from the graph. And going to the graph, we would identify where 6 hours are along our x-axis. We would follow that up to our prediction line. And then we'd follow it over, and we'd see that according to our graph, the relationship should be, or the desert temperature should be 135 hours after the sun has come up and baked that land for quite some time. Based on the equation in part B, what would the temperature be after 6 hours? So after 6 hours, using the equation we wrote, we'd have to suggest that the temperature is going to be a result of starting at 45 and adding 15 degrees every h number of hours. In this case, since we want to know how much it's going to measure after 6 hours, we simply have to substitute 6 in place of x or h and evaluate. 15 times 6, I believe, is going to be 90, and 90 plus 45 is going to be 135, and you could have done that on your calculator. So we're getting the same exact information from our equation as we got from our graph, which we should. It should be consistent. What ends up happening, though, is that graphs are somewhat limited based on size, but equations aren't. They can go into, or they can predict at any unit of time we'd like. So in part C, we're asked, what would based on the equation, what would the temperature be after 14 hours? 14 hours, again, would be difficult because our x-axis doesn't quite get there, and we'd really have to extend and extrapolate or push that line well beyond what we were prepared for. Not a big deal. We could simply say the temperature should start at 45 and go up for 15 degrees for 14 hours. So we'd have to evaluate that on our calculator, and I believe that we're going to get 255. I'm going to have to check my work there. And that would be really stinking hot. I think I usually describe this as like my Mars example. Yeah, maybe the sun is out for 14 hours straight in a desert on Mars, and it gets up to 255 degrees. That is a hot planet. So T equals 255 degrees after 14 hours. Okay, flip, take a look at the back. On the back, everybody gets a tiny bit more complex, only because as you're trying to put your relationship to slope-intercept form, you're going to have to use a few more algebraic steps. So when you take a look at number 3, in order to solve for y, we want to kind of go backwards through PEMDAS. We want to undo the order of operations surrounding the term that y is included in. So y is included in the times 5, but we're subtracting 10x's, and that's the addition and subtraction we want to undo first as we reverse engineer this question. So we're going to add 10x's, do the opposite of subtracting 10x's from both expressions. And we get 5y equals. Careful here, don't be that kid that tries to slam negative 15 and positive 10x together. They're not like terms. They do not include the same variable, raised to the same power. Negative 15 doesn't have an x at all. So you'd have to write this as either negative 15 plus 10x, or if you prefer, you could use the commutative property and say 10x less 15. We don't want the value of 5 y's, we want just 1, so we're going to undo multiplication with division. Make sure you divide the entire expression on the right by 5, which is equivalent to multiplying by 1/5. And the result is going to be that y is equal to 2x less 3. Identifying this as a linear in slope-intercept form, and it's linear because x is being raised to the first power. Please don't forget that. It's a first-degree polynomial. Y equals mx plus b. M is the amount being multiplied by x, whether it is in what we call standard form, or if it's presented as negative 3 plus 2x. M is still the amount being multiplied by x, so the rate of change is that we're increasing two measured amounts every 1 unit at a time. And for graphical purposes, that's going to be identified as the rise over the run. The beginning amount's the value at time 0, and that's always going to be the constant numerical value. And it's a good idea to write it as 0, negative 3. What that really means is that if we substituted 0 in place of the unit of time, we added 2 0 times to negative 3, what would the value of the expression be? Well, 0 plus negative 3 is just negative 3. Anything plus 0 is just itself. So we're able to then go ahead and graph. And in doing that, we're going to start at 0, negative 3. Start at time 0, label your axes x, y. Don't go left or right from the origin, and go down 3 units. And then we're going to follow a rate of change of up 2 and over 1. Up 2 measured amounts every 1 unit at a time. You can plot that across your graph. And then we're going to reverse the pattern to get points in what I call the back of the graph, or prior to time 0, so points in the past. If we want to go backwards in time, we want to undo addition with subtraction. We're going to go down 2 measured amounts and over 1 unit at a time. Usually put a little x there. Down 2 measured amounts over 1 unit at a time. Down 2 measured amounts over 1 unit at a time. You can put whatever representation you want. Some students like to put tiny little circles so they don't see them too much. And we're going to use a straight edge, either the side of our ruler, or the side of our calculator, or something that we were able to get our hands on. We want to include arrow tips on either end. And we want to label the graph appropriately. This was the relationship that started at negative 3, and we added 2 over and over again to show a picture representation of this repeated addition pattern. There's your training question, and we go right into our context question. So for our context question in number 4, we're trying to observe the balance in an account based on some monies and some repeated additions that are happening. Good idea to label your axes x and y. Y is measuring the balance in account in dollars, and x is measuring weeks. What a surprise. 90% of the time, the x-axis is time. In order to solve for the y variable, we need to solve for b. And in order to solve for b, we need to work backwards through order of operations. So we're going to undo the addition and subtraction that is happening to the term that b is included in. That's going to require us to add negative 500 w's to both expressions. Or if you prefer to say subtract 500 w's, you are correct. Subtraction is the same as adding the opposite. And we get 8b is equal to, you got to say negative 500 plus 4,000. You're not wrong if you say 4,000. Subtract out 500 weeklies. And I say weeklies because right now it's represented as 8 weeks. So let's undo the multiplication of 8 and divide by 8, or multiply by 1/8. Division is the same as multiplying by the reciprocal. And I'm going to do that on my calculator just because I don't want to do it on my screen because I'm still having difficulties. So 4,000 divided by 8 is 500. So we're able to identify this relationship as increasing 500 starting at 500, excuse me. And we notice that it is decreasing by 500 per 8 weeks. So you're not wrong if you were to write a decrease of 500 every 8 weeks. But I do want to simplify that fraction. Once again, I'll do that on my calculator. So we don't want the value as per 8 weeks. We want the value each week. Therefore, we're going to divide out the coefficient of 8. And when we divide 4,000 by 8, if I do that on my calculator, I get 500. If I divide 500 by 8, I get a decrease of $62.50 per week, which is going to be difficult to graph. So I'm going to use my math function key to turn into a fraction on my calculator. And when I do that, it's going to simplify it. It's going to say, well, why don't you represent that as b equals start at 500, and decrease by $125 every 2 weeks. And I'd prefer it as a fraction in simplest form rather than 62 and a half, because it's going to be a lot easier to interpret a decrease of 125 every 2 weeks as in rise over run form. So now that we have in slope intercept form, we do want to say that our beginning amount at time 0 is 500. That's the constant numerical value in our linear expression. And the rate of change is a decrease of $125 every 2 weeks, and that is in fact our rise over our run. Starting at 0, 500, I'm able to show that this is going down 125 every 2 weeks, and I have to investigate the scale of the x-axis to interpret how to appropriately represent my rise over run, or my rate of change. And what I notice about this is that in the x-axis, or the y-axis, excuse me, every 2 boxes represents 250. What I notice in my y-axis is that every 2 boxes represents 250. And because every 2 boxes represents 250, that must mean that every box is 125. So I go 125, 250, then I must go 375, 500, then I must go 625, 750, and so forth. So in order to appropriately represent the decrease of $125 every 2 weeks, I have to go down 1 box, which is $125, and over 2 weeks. Down 1 box and over 2 weeks. Down $125 and over 2 weeks. Down $125 and over 2 weeks. I could then use a straight edge or a ruler, and I can connect those points to show the decrease in these monies over time. Maybe that represents bills somebody's paying, or I always like to talk about college students. I feel like college students right now aren't having the typical experience they normally would. So a student goes away with $500 between Thanksgiving and Christmas, and they have to make it last for some time, so they're spending at a rate of $125 every 2 weeks. In part B, we're going to see more of this tomorrow, actually. We're asked to graph a line that is parallel to the one we just graphed. And in this particular line, we're told that the rate of change is the same. We're going to learn that tomorrow. Parallel lines have the same slope, but the beginning amount is different. So we have a rate of change similarly or identical to the previous relationship of a decrease of $125 every 2 weeks, but the beginning amount in this instance is $875. We're going to learn parallel lines have the same slope, so they look similar. They just start at different points. $875 would be in between $750 and $1,000. And it also is going to go down 1 box every 2 weeks because it has the same slope, same rate of change. And this might represent a student who went away to college with a little more money in between Thanksgiving and Christmas, but intends on spending at the same rate. Maybe they want to save some of that money for when they come home and they're going to buy holiday gifts for their family. And you can get this relationship. And if you actually label those relationships appropriately, here's what you would see. You would see that the first one could be identified as our balance. Starts at 500 and decreases by $125 every 2 weeks. And our second relationship starts at $875 and it goes down $125 every 2 weeks as well. As we go on down, the last training question, if you want, you can give that a shot on your own. You can pause the video, and then you can see if you're able to actually take a linear relationship. We know it's linear because it's x to the first degree is polynomial, and solve for y and graph appropriately. Give it a shot. Hopefully you're able to get a good look at that on your own and have some practice in taking a linear relationship not in slope-intercept form and solving it for y appropriately. Therefore, you can see it as y equals mx plus b, and you can identify how the measured amounts y are changing with respect to all the other items in the relationship. So we needed to get the relationship using appropriate algebraic steps to present itself as y equals mx plus b. That's going to require us to undo order of operations, and we're going to undo addition or subtraction first. So I chose to add positive 3x's to both expressions. Then I didn't want the value of the opposite of 4 times y, so I divided out the coefficient of negative 4 from both expressions, making sure I divided the entire expression on the right by negative 4. 3 divided by negative 4 is best written as negative 3/4. You're not wrong if you said, Tooch, isn't that negative 7/500 x plus 2? But that is correct, but you're going to have a hard time graphing a decrease of negative 7/500. You're better off leaving it as negative 3/4. That's going to be easier to interpret as rise over run. The beginning amount, the value times 0, is the constant numerical value. Careful, negative 8 divided by negative 4, negative divided by negative is a positive. That should have been 2. This relationship should have started at time 0 at a measured amount of 2, and we always begin graphing along the y-axis. That's why we call it our y-intercept. And we're able to identify that at time 0 it measures 2. And then we can follow our rate of change or our slope. We can decrease this measured amount every 2 units of time, every 3 units of time going over 4. Decrease 3 measured amounts every 4 units of time. We can reverse the pattern. And to go backward in time, we would undo that subtraction with addition. We'd add 3 measured amounts and go back 4 units of time. Add 3 measured amounts, go back 4 units of time. And this is a pictorial relationship of the measured amounts in a linear pattern that starts at 2 and is decreasing by 3 over and over again. In a table of values, this might present itself as at time 0 it measures 2, Then we might see that at time 4, it measures -1. Then we might see that at time 6, 7, 8, it measures -4, and so forth. And you notice that every 4 units of time, the relationship is going down 3, changing y over changing x. And lastly, we have our context problem, and this is a great one for you to try on your own as well. So again, let's just make sure we get you set up, and then you can give it a shot to see if you understand how to perform the skill. So we're looking at linear relationships where they are not in slope-intercept form, and you have to begin by solving for the y variable in order to graph appropriately to identify m and b. So in this case, it would be a good idea to begin by labeling your axes x, y, identifying the fact that we are measuring, in this case, g, which is representing a particular hormone in someone's body, and that is happening in comparison to days. What a surprise. 90% of the time, the x-axis is time. So I need you to solve for g with appropriate algebraic steps, identify the rate of change as well as the constant numerical value, and graph appropriately. Give it a shot. Assuming you understood the process in question number 6, you were solving for the variable g, which is the y component. So we want to get this relationship in an appropriate form or formula to graph, which would be solving for g so that it appears as y equals mx plus b. And in that instance, we would have to undo the subtraction of 200 units of this hormone per day, adding 200d to each expression. You can add whatever you want to an equation, so long as you do it equally on both sides. That is the additive property of equality. 600 plus 200d per day is just 600 plus 200 per day. You cannot put those quantities together. They are not like terms. They don't have the same variable rates, the same power. And we don't want triple times the value of g as it relates to the other amounts in the relationship. We want just 1g. So we're going to undo multiplication with division. 3 divides to itself perfectly one time, leaving us with 1g. And we have to divide the entire expression on the right by 3 as well, leaving us with 600 divided by 3 is 200. We're starting at 200, and 200 divided by 3 is going to be a repeating decimal, so I'm going to leave that simply as 200 unit increase every 3 days. 200 over d. That way when I interpret it as slope, rise over run, it's going to be easy to understand how I'm increasing over and over again. When I graph it, I will begin at 0, 200 along the y-axis. That is where the y-intercept occurs. It's the value at time 0. And I'm going to follow a rate of change increase of 200 units of this hormone every 3 days. 200 units every 3 days, 200 units every 3 days. I will connect that with a straight line. I must have an arrow tip in the end, and I should label it appropriately. For part B of the question, it says, based on the graph above, how much HCG should there be after 10 days? After 10 days, ladies and gentlemen, we would have to identify that along the x-axis. We would follow that up to our line of prediction. It appears to be just under a grid line. So as I follow that over to my y-axis, that looks to be a little less than 900. So I suspect maybe 875. That's going to be my best prediction, units of HCG. Ladies and gentlemen, this was the lesson on graphing linear relationships in slope-intercept form when the original presentation of the relationship is not in slope-intercept form, when you actually have to solve for the y variable to better see what m and b are. Hope it went well. I'll see you in class. Take care.